So today is September 6th, and it is, this class is interesting. Like, we've never done this class this way before. 2 years in one, okay? You don't. You get the 1 credit. The idea is that you'll still have 4 years of math when you're out of here, but perhaps you can also get 6 college credits as well, which would be very cool for some of you. Some of you will get 3 college credits, and some of you will get 6. Depending on how old you are, you could take AP Calculus, in which case you'd earn 3 credits if you pass the test.
3 college credits?
Mm-hmm.
Are you crazy?
And then if you're a sophomore right now, then next year you might take AP Calculus, and then the year after BC Calculus, which again, if you pass, we will next year.
Oh,
yeah. So if you are a sophomore, then you might end up in BC Calculus, and you would get another 3 credits of math out of the way. Which for almost, I would say 90% of majors, you've met and beyond your math requirement. So any of you that are, I expect all of you are going to college, and I also expect all of you are going to be in some sort of science field. So if you're going to be in any sort of hard science field, then you'll probably need 1 more math class, okay? Which would be vector calculus, which is super fun.
Even our teacher who does calculus for fun says rolling.
Yeah, it's fun. All right. Okay, so for those of you that weren't here yesterday, we found out something very cool. We found out that not only can I write the square root of x like this, where there's a little 2 in the index there, but it has an equivalent form. So what's the other way that I could write this? X to the 1/2, okay? So rational exponents, rational fractional exponents translate back and forth between radicals. So if I wanted the cube root of x, that could also be written as x to the 1/3. And so we learned some very interesting thing. And the nice thing about exponents is that our properties that we learned with exponents so also work when we have rational exponents. So if I have something where I want to multiply these together and they have the same base, what are we allowed to do to the exponents? We're allowed to add them together. And of course, the only thing we need to remember is the base stays the same. We add those exponents together. They need to have a common denominator now. What is 1/2 plus 3 halves? 4 halves, which would be x squared, which is very cool. So this today, again, is sort of another kind of interesting day. Really interesting, actually. Today, we want to simplify in the most simple form. And so today we have something that we want to talk about. I want to introduce right now, which is the cube root of x to the 4th. We did this. We know how to simplify this. And so before, if we were trying to simplify the cube root of x to the 4th, we would break it apart and we'd say, hey, that's x cubed times x to the 1st. Remember me doing that? And what is the cube root of x cubed? X. Good. And then I don't know the cube root of x to the 1st, but so that stays in the radical. Okay. All right. So you know how to do that. Well, the nice thing is it works really well with rational exponents as well. So this was the old way from a few days ago. But here we have another way, same thing. I want to translate this to a rational exponent, which means it's going to be x to what? 4/3. Very good. And if it's x to the 4/3, here's a really interesting thing. Isn't that the same as 1 and 1/3?
Yeah.
Yeah?
Yeah.
Which would be x to the 1 plus 1/3, yeah? You guys so far? You good? You with me? We're sort of going in reverse here. And what property allowed me to add exponents? Yeah, okay. So this is x to the first times x to the 1/3. Which, isn't that the same as this? Interesting. Okay. So when we have, shall we say, an improper rational expression, it's heavy on top, bigger on top, then we can do some simplifying. And so you can think about it either way. You can think about it in terms of taking roots, or you can think about it as just simplifying with powers. So this is x times the cube of x. All right. So we are working both ways today. Let's see what else. Example 1, perform the operation. Express answers in simplest form. Oh, look at it, I just did that one. It's funny. Most of you weren't writing that down, so I guess it's good I have it again. Express answers in simplest radical form. And again, simplest radical form means if we can take the root, or if we need to rationalize, we might need to do that. So we have to really think this through today. So we might need to rationalize. Okay, so I have the cube root of x to the 4th, and I'm going to do this with rational exponents because that's what we're trying to practice here. That's going to be x to what power? 4 over 3. 4 over 3. Power over index. So the index is 3, so power over index, 4 over 3. All right, so that is the same, wait, this slightly differently, as x to the 3/3 times x to the 1/3. Why is that true? Yeah, because if you have the same base, then we would add those exponents together, and that's how we get 4/3. And then, of course, x to the 3/3 is really just x, and x to the 1/3 is really just the cube root of x, yeah. All right. The general math rule is if it starts in radical form, then we want it to end in radical form. So that's why I put it back into radicals. This one, a little different, a little harder. We're still multiplying two things together. And again, I'm going to go and convert it using rational exponents. So this is going to be x to what power? 2/3. Very good. Power over index, 2 over 3. Good. Times x to what power? 1/2. Very good. The index is 2. We got a power of 1. So 1/2 power over index. Now I can simplify these a little bit. They have the same base. What do we need to do to our exponents? Add them. What do we need in order to add them? Common denominator. So that would be 6. So that's going to be 4 over 6 plus 3 over 6. Whoops. I'm doing things in my head ahead of time. And so that gives me x to what power? 7 over 6. Good. And 7 over 6 is x to the 6/6 times x to the 1/6. Very good. And x to the 6 is x. And then x to the 1/6 would be the 6th root of x. Interesting. It is weird. Well, so the interesting thing is, like, this particular problem, because the indices are different, one's a cube root and one's a square root, it's hard to figure out how to simplify those. But when we convert them to rational exponents, then the math sort of just takes care of itself. It's kind of interesting.
Didn't you just multiply the index by yourself?
So yeah, so that's where we get the 1/6 from. That'd be another way to do it. So if you multiply those, you'd get the 6th root of x cubed. That's different, isn't it? Yeah. So there's something weird that's happening in there too. So we'd have to investigate that. All right. Letter C. We have the 4th root of 3 times the cube root of 9. These don't have x's and y's, do they? No, these are numbers. So, all right, I'm going to say it seems harder. Yeah, right. A little bit. So this is 3 to what power? 1/4. Good. 3 to the 1st. The index is 4. Okay. And then this would be 9 to what power? 1/3. Very good. Now, over here, they were x's. They were the same base, right? These aren't. But could they be? Oh, what can we do with the 9? Well, I can rewrite. I can't divide. This isn't an equation. We're just simplifying things. So I can change the 9 into something equivalent. 1/4. That 9, isn't that the same as 3 squared? So that 9 I can replace with a 3 squared, and it's still to the power of 1/3. So again, I still have exponent properties. What do these power raised to a power do? They multiply, yeah. So this is 3 to the 1/4 times 3 to the 2/3. Yeah, this would be 2/1, if you will, and you multiply straight across. So 2 times 1 is 2, 1 times 3 is 3. Okay, now these have the same base. So what can we do? Get a common denominator and add those powers together. Good. Common denominator is what? 12. So that's going to be 3/12 plus 8/12. 3/12 plus 8/12 is 11/12. And that is not top heavy. So that doesn't simplify anymore. Does top heavy make sense to you? Yeah, it's actually a regular fraction, not an improper fraction. So this one, I'm just going to go ahead, and this is the 12th root of 3 to the 11th. Yeah. 3 squared right here. So 3 squared is the same as 9. And then what we did was we said this is a power raised to a power. So we multiply those together and it combines into that 2/3. Yep. All right. Isn't this stuff crazy? It's crazy weird, right? I can zoom some, yes. Okay. Is that better? Okay. All right. So this one. All right, I'm going to convert. Again, in higher math, we never use radicals. We just don't use them at all. And I know this is your first experience with these rational exponents. So Don't worry if you're like, ah. So I can rewrite this numerator as 4 to what power? 1/3. Excellent. At this point, I'm kind of like, if you get that, then great. That's exactly where you should be. And then I can rewrite the 2 with 2 to what power? 1/2. Very good. Now again, when the bases match, I can combine. So, but these bases don't match, right? They could, yes. Very good. So I can do a little bit of changing around here so that my bases do happen to match, because that's kind of key. What can I change the 4 out for? 2 squared. Very good. But it's still raised to what power? 1/3. Very good. And so then, again, we're in the power to a power situation. So that's going to be 2 to what power? 2/3 over 2 to the 1/2. So now these have the same base. So what are we allowed to do? Subtract the exponents. And we do that top minus bottom. So we, again, need a common denominator. What is 2/3, the common denominator? 6. So that's going to be 4, 6 minus 3, 6. Good. Which is 2 to the 1/6. And again, this exponent is a regular old fraction. It's not improper. And so it doesn't simplify anymore. That's going to be the 6th root of 2. There you go. So that's a good question, and I don't think you're going to have any like that. Yeah, because this is the perfect world of math class. Ultimately, if you had this, you'd use your calculator in the real world and just get a decimal approximation. So, Noel. Square the 2. Where are you?
Instead of
make it a 4.
Instead of the 4.
No. Oh, yeah. So you're saying, can I change this 2 to a 4?
Yeah.
Okay. So question. To change this 2 into a 4, wouldn't you have to multiply by 2?
It's square.
So does that, remember, this isn't an equation where you can square the left and the right to square both sides. So if you were to just change one thing, that would change the value of what we're starting with, right? That's a really good question, and I love when you guys ask those kinds of questions, because that's what we want to always have in our mind. We've got to make sure we're not changing something when we do our algebra. Those are all skills that we are going to use at the opportune time. But yeah, what we're doing is I'm replacing 4 with what it's equivalent to, which is 2 squared. Which is not to say that's the same as, it's not the same as dividing by 2 either. All right. Okay. Blessing. I tried it. Rationalize the denominator. Rationalize the denominator and express the answer in simplest radical form. Rationalize the denominator. We have 3 over the cube root of y squared. And again, we've done this with with radicals, but I want to show you how to do this using those rational fractional exponents. Okay, so I'm going to go ahead here. We've got a 3 on top, and I want to rewrite my denominator using a rational exponent. So it's going to be y to what power? 2/3. And again, the nice thing is when we use rational exponents, I want this to turn into y to the first power. And then I'll know it's rationalized. I'm going to multiply top and bottom by y to some power. No. 1/3. 2/3 plus what gives you 3/3? 1/3. Yeah. So y to the 1/3. I'm going to multiply. So how come I'm allowed to multiply by y to the 1/3?
Because it's equal to 1.
Because it's equal to 1. I'm doing it to top and bottom. It's equal to 1. All right. And because these have the same base, we're allowed to just add those exponents together, which is super nice because that gives me y to the 3/3, which is just y to the first or y. And on the top, we have 3 times y to the 1/3, which is just 3 times the cube root of y. That's rationalized. It's kind of easy to just add what you need to make it whole. Math, it's crazy how it all works. Crazy cool. Okay. Letter B is a much more of a challenge. I don't think any of yours in your homework are as hard as letter B. All right, I'm going to rewrite again using rational exponents. So this is m to what power? 1/2. Very good. And in my denominator here, I have a 3. And then this is n to what power? 2/5. All right, so it's 3 times n to the 2/5. So the problem is I have a radical in the denominator, and it needs to resolve. So I need to multiply top and bottom by something so that this becomes into a whole fraction. 3/5. Very good. You guys catch on so quick. All right. Okay. So my denominator, there was nothing wrong with the 3. The 3 was totally fine. We didn't have to do anything with that. So we get 3 times into the 5/5. So 1, yeah. And then up here is where we're going to do something very weird. And again, there's nothing that's hard in your homework. What I want to do is actually, I'm going to rewrite them so that they have a common denominator.
Same base.
I know, they're not the same base. Hold on to that thought. So, what is the common denominator? 10. So that's going to be m to the 5/10 times n to the 6/10. Okay. Now, they don't have the same base. Here's where it gets really weird. These two things are multiplied together. Watch what I do. See if you can see what happened.
Oh, shoot.
What did I do?
You just split it out.
I took out the 1/10, yeah? So we have, remember with our exponent, I know this is where it's like you use properties in reverse and it's like this whole crazy thing, right? I'm pulling off the 1/10 because our exponent property says if I have a power raised to a power, they multiply, right? And so if I were to do this our normal way, we would say this would be 5 times 1/10, which gets us the 5/10, and 6 times the 1/10, which gets us the 6/10. So now, going back to radical form, this is a 10th root of m to the 5th into the 6th over 3n. Oh my gosh, that one is crazy.
That's just an extra step for no reason, in my opinion. But this is.
I don't know. I probably need to do it around you.
I mean, if you can go from here to here, great. But it took me. I was like, say what?
I was
So, yeah.
I looked there and I'm like, oh, just Saturday.
Right? It's weird when we do stuff in reverse. Okay, ladies and gentlemen, have some fun playing with these.
Oh my god.